Hey guys, this video is for me to finish everything that I know on section 2.1, which I'm supposed to finish last Monday. I'm really sorry that I didn't finish that. Um, I checked with Professor Raphael yesterday, but still there's a lot of things that I don't understand. Um, so if you think it's necessary, we can go to Raphael together, maybe sometime today. Okay, so I'm going to talk about three things. The first one is affine space, and the second one is the paragraph in the first several paragraphs in page 62, and the third part is the proposition 2.1.7. But for the second part, Raphael didn't say anything about that, and I can only tell you my understanding about this one, which is probably not true. But yeah. Okay, so let's do the first one first. The first one is called the affine space. So basically, according to him, a affine space, it means a constant plus the linear space. Constant plus the linear space. Which means that, well, if you have a vector in linear space, let's say v1 plus a constant, then this is going to be, this constant is not equal to 0. And this vector is going to belong to this affine space. And suppose we have two vectors from the affine space and we add them together, and then we will see it is going to equals to v1 plus v2 plus 2c, which is not belongs to the affine space that we defined before. But if you do the convex combination, and you get lambda. Lambda is a constant that is greater than 0 but smaller than 1, minus lambda times v2 plus a constant. And this is going to give us lambda times v1, v1 and minus v2 plus lambda c minus lambda c and plus c, so that's going to be c. This belongs to the linear space, and this is the eigenvector. This is the constant, so this belongs to the affine space. So affine space is closed under convex combination, but not closed under the general sum. Okay, so I'm gonna do the third part first, which is the proposition 2.7, 2.1.7, and do the second part later. Okay, so in 2.1.7, like I said before, in general, we need to break the interval from 0 to 1 into the union, and from negative infinity to infinity of phi and a to phi and a. And for each single interval here, for each single interval here, let's say, we will have a map H, which is defined as psi n compose capital H compose phi to the negative 1. This is defined from phi n of a, phi n plus 1 of a to psi n of a 7 plus 1. So let's look at it in more detailed way. So when n equals to 0, then we have, let's denote this by h0 is gonna equals to h, right? And this is from this is from a to phi, from this interval to the interval a to psi of a. Okay, so when n equals to 1, we have h equals to psi compose h compose phi inverse. This is from, again, sorry for the slow handwriting, to this. And from here, let's denote this by h1 since it is a map from this interval to this interval. Okay. So in this case, we have h1 compose phi equals to psi compose h. Right. Let's do another thing again. If n equals to 2, sorry, h2 is gonna equals to phi squared. Maybe in another way, phi compose phi. Sorry, psi compose h compose phi inverse compose phi phi inverse, and this is gonna be from phi 2 to phi 3 to psi 2 to plus psi 3. And if we move these guys back to the left, you will have h2 compose phi equals to psi compose h. And as we know here, psi of h equals to this guy equals to h1 compose phi. And if we compose phi inverse on each side of the equation, we'll get those two phi's cancelled out. And all we know is h2 compose phi equals to psi compose h1. Right. And we can do it again and again and again. For the general n, we'll have hn compose phi is gonna equals to psi compose h n minus 1. Since n is from negative infinity to infinity, if we take the union, let's see, h is defined as the union of hn, where n is from negative infinity to infinity. Since each single hn is map or interval to another interval, and their union is gonna be map 0 to from map the interval in 0 1 to the interval in 0 1. And if we do the union, and we'll get h compose phi is gonna equals to psi compose h, right? Since it's n minus 1, it doesn't really matter since we take the union. And from here we know that phi and psi are conjugate. Okay, so this is the things for the second part, for the third part, and let's do the second part. This is just my understanding. This part, and yeah, if you don't approve it, you can just stop watching it, and maybe we can discuss it later. Yeah, there's Refu didn't mention this part, and all I get is my understanding. So basically, this part is saying that if we have a phi here, that is a map from 0 to 1, which satisfies those properties. 0. And based on the first sentence in query under the query 2.1.5, we know that the analytic contracting map preserve a affine structure here and here. Why is that? Raphael said that we don't really need to understand it. It's just fancy language. That's what he said. I don't know. Okay, so if we have a affine structure here and a affine structure here, and the statement is that there's infinite dimension space of moduli such that the transition map just the transition map provides the infinite dimension space of moduli. So I'm gonna do it in the way that the book did. So the first step is to find the base point. Let's denote the base point by A, and then we have our map restricted at this point as the interval from A to phi away. So let's say, well, maybe this is A and this is phi away, and then we have this curved segment here. How to change the color? Sorry about that. I don't know how to change the color. Oh, here. So this is the lines. This is the line segment that we want. I mean the curve segment, something like that. And we denote it here. And this is from A to phi. This is A, this is phi away, and this is phi away, this is phi squared away. And we normalize it, which means that we expand it vertically and horizontally to make sure that the original map becomes a map that is from 0 to 1. From 0 to 1. Maybe 6, 1, 1. So this is the definition for phi of A, phi of T, which he wrote in a long sentence, phi squared, something like that. So the basic idea is to change it by coordinates change and expanding to make sure that it is a map from 0 to 1 to 0 to 1. And the next step is to extend it. The way to extend it is that phi A of T plus K equals to phi A of T plus K. So basically, I think the idea is that if we have our let's draw phi away. Let's draw this function first, the normalized function for phi away. And we'll see again it is gonna be our function that looks like this. This is 1, this is 0. Sorry, I need to redraw it again. So suppose we have a function. This is a normalized function for 0 to 1. Sorry, this is 1. This is 1. And we do it again. And by the definition of the extending thing, equals to phi of a phi of t plus a constant k. Then when k is equals to 1, then we have this. And when k equals to 2, we have this again and again and again. And based on the definition for equivalent in the book, so equivalent means that if we have two diffeomorphisms phi and psi, and they all satisfy the condition that psi of 0 equals to phi of 0 equals to 0, and also maybe psi of t equals to phi of t plus a constant s minus phi of s, where s is some. If this equation holds for some s, and s is belongs to 0 to 1. Okay, so if we look at the picture here, then we can say that suppose this is our phi. Suppose this is our phi, phi of t. And then we have phi of s. Phi of s is just a, this is s, right? And what is phi of t plus s? So it's just to move the whole function to the left with the length s. So this is s, negative s, and we just shift it a little bit. We'll get something like this. This is phi of t plus s. So what is phi of t plus s minus phi of s? So I'm sorry, those cut has to be in the same line. So this is phi of s. And phi t plus s minus phi of s is just things like this. All the things along here. So the function, well, the function phi t plus s minus phi of s, which is our psi of t, which is gonna be something that, according to my understanding, is gonna be something like this. Right? I don't know. You tell me if it's right or not. And basically, that is everything that I know. And what the book is trying to say is that a change in the base point replaces the transition map by an equivalent one, which means that probably if we change a, if we change a, then phi b, maybe change a to b, maybe, and phi b of t is gonna equals to phi a phi of t plus s that exists as such that phi minus s minus phi a of s, this thing holds, which means that phi b has to be something that looks like the red curve that we have here, but I don't really think that is true. So if you have any better ideas, please let me know. I really want to know why the book says that. Okay, so thank you for your time, and hopefully you learn something from here. And I'm really sorry that I can't figure this out on my own. See you this afternoon.